Welcome back, students. In this video segment, we're going to start Chapter 2. Specifically, we're going to take a look at Section 2.1, Vector Spaces. I want to talk a little bit about the chapter generally. This chapter and Chapter 5 are probably representing the most difficult parts of this course, chapters in this course. Some students find Chapter 2 more difficult than Chapter 5, some the other way around. The reason I'm bringing this up is that I want you to prepare to spend an enormous amount of time on this chapter. Okay, a lot more time on this chapter. You'll probably spend a lot more time on this chapter than any other chapter in the text. Also, we're going to be talking about operations of addition and scalar multiplication. And what's going to be very important for you is that you put aside your ideas of what addition and scalar multiplication mean when it comes to vector spaces, because the concepts of addition and multiplication are not necessarily the same as the concepts of those two operations for real numbers or complex numbers, okay? I think I'll be repeating that as we go along, so if that didn't make any sense to you right now, it probably shouldn't. We need to start this very long section, actually. We need to start this very long section with some definitions of logical symbols. Some of you may be familiar with these symbols. Some of you may not be. In fact, I would imagine most of you are not too familiar with most of these symbols, but they're universal symbols. So logical symbols. Okay. The first logical symbol that we're going to look at looks like an upside down A. Okay. What it means is for every, or for all, for each, or for every, for all, for each, or for every. Okay, we have also a backwards E that stands for there exists. There exists. Okay, or there is. Okay, there exists, or there is. A backwards epsilon, Greek epsilon, means such that. Such that. Yeah, I'll be giving you some examples in a minute of how to use these. The forward epsilon, the regular epsilon, means is an element of, and you can remove the word is if it's necessary. You can just interpret it as an element of, or a member of. Some will read this as is in. Okay. Again, I'll be giving you some examples of this very, very soon, so hold on. We also have a 0 with a slash through it, forward slash through it. This is the empty set. Empty set. What is the empty set? It's the set that has nothing in it. That's all it is. It's the empty set. We have the 3 dots forming a triangle, and those mean therefore. Therefore. Okay. There are a few other logical symbols, and I'll mention those in a few minutes. Right now I want to take a look at some specific examples maybe using these symbols. So examples. Let's say example A, part A. for every x in R, for every x in R that is an element of R, or for every x an element of R. What is this saying in better English? It's saying for every real number x, for every real number x, for every x in R, comma, there exists a y in R. So for every real number x, there's a corresponding real number y such that, backwards epsilon, y is greater than x. Does this make sense to you? If not, here's a number line. Check it out. Here's a number line. Put 0 here. For every x, so there's one. There's an example of one. There exists a y such that y is greater than x. For every real number you can pick, I can find something more than it. That's all that that's saying. For every real number that you choose, that can be chosen, there can be found another number that's bigger than it. Now, there are a lot of numbers that are bigger than x. The existence just merely means that there is at least one. So the existence of something means that there is at least one thing. It doesn't mean that it's unique. It doesn't mean there are an infinite number of those quantities or things or items that you're claiming existence. It just means there is at least one something. So the backwards E means there exists, and that existence doesn't mean unique, exists a unique or only one, okay? Okay. So let's take a look at another one, another example. Let A be the set of all x in R, the set of all x in R, such that x is not equal to x. It's a set of all real numbers that are not equal to themselves. What can you say about this set? Clearly, A is empty. Clearly, A is the empty set. There's nothing in it. There's no number that's less than itself. Okay. I'm sorry, there's no, oh my goodness, there's no number that is not equal to itself. Okay, so C, I don't know why I said less than. 3 is less than 4. Therefore, 4 is what? Greater than 3. Okay. Okay, so another example. True or false? True or false? Let's say A for part A for this example. For every x in R, for every real number x, there exists a y in R, such that x plus y equals 0. True or false? For every real number, I can find another real number, such that when you add those real numbers, you get a 0. Of course, that's true. For every real number x, I can find another real number y, such that x plus y is 0. Yeah, it's called the opposite of x. Okay, proof. In this chapter, we do a lot of proof. A lot of proof. That's why we were looking so heavily at proofs of matrix properties. Mostly the proof of the matrix properties was to get you ready for formal proof in vector spaces. Okay, so this is why you studied proofs in vector spaces. Okay. Okay, proof. I want to prove that for every real number x, I can find a real number y such that x plus y is 0. So let x be a real number. Start out with a real number. Which one? I'm not going to say. This is supposed to be true for all x. I'm just picking an arbitrary real number. When you're trying to prove something about the existence of something, that means you have to find it. You have to find something. So what would be the word that I would use to continue? When you're trying to find something, when you're trying to prove the existence of something, the word that you need to use, the next word you need to use is choose. Choose. If you're saying that for every real number x and r, there exists a y and r, that means you have to find it. Or one of them if there's more than one. So choose. Choose y to equal the opposite of x. Then finish the proof. X plus y, I need to equal 0. Well, that's x plus, well, I've chosen y to be the opposite of x, and x plus the opposite of x is 0. QED. Okay. B. Still true or oh, well, so it was a true or false question, so I guess I should say true. True. That's the ugliest looking T. Well, I guess it gets the job done. It doesn't make it any less ugly, though. So that's a true. So B. For every x in R, comma, there exists a y in R. For every real number x, there's a real number y, such that x times y equals 1. So for every real number, for every number that you can imagine, can you find another number so that when you multiply x by it, you get 1? Excuse me. Well, the tendency is to say, well, yeah. For every x, all you choose for y is the reciprocal. X times it, a number times its reciprocal is always 1. What I just said is false. This is a false statement. False. Why? This is saying for every real number, this is saying every real number has a reciprocal. No, which real number doesn't have a reciprocal? 0. So the statement is about for every x. Okay, so I claim that this is false. So there must be an x for which this is false. So choose or let x equal 0. If the statement is supposed to hold true for all x, then it needs to hold true for x equals 0. So there does not, to negate a logical symbol, you put a forward slash through it. There does not exist a y in R such that xy equals 1. Okay, since, well, substitute 0 in for x. 0 times y equals 1 has no solution. There's no way to find a solution to the equation 0 times y equals 1. Okay. Okay, we're almost done with we haven't started the chapter yet. We're just looking at the logical symbols that we're going to be using for the rest of this course. Okay, so more logical symbols. More logical symbols. A double arrow B, or A arrow B, means if A, then B. Okay, be very careful about reversing this. If it's true that A, if A, then B, it's not necessarily true that if B, then A. Okay, we'll come back to that in a minute. You could also interpret this as A implies B. If A happens, then B happens. That's how you could also interpret this. Okay, now back to what my caution. If I jump off the roof, and that's kind of gross, this example, then I die. So A is the event, I jump off a roof. B is the event I die. So A implies B. If I jump off a roof, I'm going to die. Now, can this be reversed? If I die, then I jumped off a roof. No. Everything living dies, including me eventually. Hopefully a long way off. I hope. If I die, it doesn't necessarily follow that I jumped off a roof. I don't plan to go that way. You cannot reverse if-then statements. A classic example for you is from Calc 2. If a series converges, then the general term must approach zero. That's true. That's true. However, the reverse is not true. The reverse is not true. If the general term approaches zero, the series need not converge. A sub n approaches zero, then the series converges is false. False. 1 over n approaches 0, if you don't remember the classic example. Oops. However, but the sum of 1 over n diverges. It's the classic example of the test for divergence. You can't reverse the test for divergence. If the general term approaches 0, you can make no conclusion about the convergence or divergence of your series. The 1 over n does approach 0, but the harmonic series, the sum of 1 over n diverges. Okay, we're getting back into Calc 2, and I don't want to do that. So, one more logical symbol, and we're ready for vector spaces. A, double arrow, B. Okay, A, double arrow, B. This means both ways. If A, then B, and if B, then A. Okay, so this is a logical statement that two things are equivalent. Equivalent means if you have one, then you have the other, then if you have the other, you have the original. Okay. It can also be stated as A if and only if B. A if and only if B means if A then B, and also if B then A. Now we are ready to study vector spaces. Before we can study them, we have to know what they are. Okay. So off camera, I'm going to write an example real quick here. So here's a question I'd like you to consider with me. What do the following sets of mathematical objects have in common? What do these have in common? The set of real numbers, the usual symbol for real numbers, set of complex numbers. You may not have seen the symbol for complex numbers, like capital C with a little line through it, or a little line added to it. The vectors from physics. If you haven't had physics, then don't worry about it. If you had Calc 3, or if you've had physics, we're talking about those things. Arrows. That's what, if you haven't had physics or Calc 3, vectors from physics are arrows. That's all they are. You might think, no, there are other things. Nope, that's all they are. Matrices. Functions. Solutions to some kinds of differential equations. That one might be a little rough for you to think about. The last one isn't solutions to homogeneous systems of linear equations. That means when the constants for the systems are 0. Okay. What do all these sets, these sets of mathematical objects have in common? They're very different sets. Very, very, very different sets. But they all have something in common. They all, in some way, behave exactly alike. You add things in these quantities, you multiply scalars by things in these quantities, and other things. In fact, these quantities have eight things that they all have in common. I'm jumping the gun. The answer, they are all called, each or all called, vector spaces. Vector spaces. Their elements, and this is going to bother people who have had physics or Calc 3, the elements in these sets are called vectors. The elements of these things are called vectors. This is really going to bother people from Calc 3, especially if you've had me. So real numbers, each real number is a vector. Each complex number is a vector. Each vector from physics is an example of a vector. Every matrix is a vector. Every function is a vector. How is this possible? How is this possible? Well, they're only vectors in their own space, in their own set. But they all behave the same way. So if you've had physics or if you've had Calc 3, this might be a little dangerous for you because you have a powerful idea of what you think a vector is. But the things that you call vectors from physics and in Calc 3 are only one example of vectors. Vectors are not all arrows like from physics or from Calc 3, okay? Those things are examples of vectors, but vectors are much more general. Okay, so what is a vector space? Okay, so let's take a look at what a vector space is. Okay, so the definition of a vector space. A vector space is a non-empty set, capital V, Okay, a non-empty set V. Now stop there for a minute. We have to be very careful. What does it mean to have a non-empty set V? It means that a vector space has how many things in it? At least one. It has at least one thing in it. So a non-empty set V is called a vector space if there are two operations. If there are operations of addition and scalar multiplication on V such that 8 things are going to follow. Now, before we get to those 8 things, a strong word of caution. The addition and scalar multiplication are not necessarily the same addition and multiplication you're used to for real numbers. The addition, there's nothing here that says that this is the same addition or even related to the addition of real numbers. The scalar multiplication, the same thing. It's not necessarily the same kind of multiplication you have for real numbers. It involves scalars. Scalars are real numbers, but it's multiplication of a scalar by it's multiplication of a scalar and some abstract quantity we're calling a vector. Okay, so don't get lost in this. We'll look at this some more. So it's a non-empty set that has 2 operations on it, addition and scalar multiplication, such that 8 things have to hold true. First thing, u plus v equals v plus u for every u and v in the vector space. Now, if you're thinking this is obvious, then you're in trouble. The reason why you'd be in, and you won't be for long, but the reason why you'd be in trouble is that what you're thinking is that, well, real numbers behave that way, so this is obvious. Yes, real numbers behave this way, but u and v need not be real numbers, and the plus sign doesn't mean addition of real numbers. The u and the v could be bananas and oranges, and God knows what we could define for the addition. Okay, so we have to put our knowledge of the properties of real numbers aside when we look at this general definition of a vector space. So 2. Okay, let's get through this. By the way, the first property is called commutativity. Commutativity. That says that addition is commutative. Commute. To commute means to revert, to be able to basically to reverse the process and not change the outcome. U plus v is adding in one direction, v plus u the other direction. When you commute to work, that means you go from home to work and then from work back to home. You end up in the same place. Okay, that's the best analogy I can give you right away. Okay, so the next property, u plus v plus w equals u plus v plus w for all u, v, and w in the vector space. Okay, again, if this is obvious to you, you're in trouble. You have potential trouble, because this is not a statement of the associative property of addition for real numbers. It's saying that the associative property of addition holds in this general sense, where u, v, and w are these completely abstract quantities, and the addition sign is some sort of addition. It need not even be related to real number addition or scalar addition. Okay. Third, there exists a 0. The 0 is not necessarily a real number. It could be a matrix, a function, whatever it could be an element of whatever vector space you're talking about. So this is not the real number 0. There exists a 0 in the vector space such that v plus 0 equals v for every v in the vector space. 4. So there's a 0 vector in there. Okay, so I'm back to our original statement. The vector space has to be non-empty. That means there's at least one thing in it. What must that one thing be at least? The 0 vector. It must contain 0, the 0 vector. Okay. Okay, 4. For every v small v in the vector space capital V, for everything in there, I can find another thing in there. I'm going to call that thing the opposite of v. This is not a negative number because I don't know what b is. B could be a banana. The opposite of a banana, what is it? I don't know. So for everything in the vector space, there is this thing we call the opposite of v, also in there, such that v plus the opposite of v is the zero vector. This is not saying a real number v plus the opposite of the real number v is 0. This is saying a banana plus the opposite of the banana equals the zero vector, whatever that thing might look like, whatever the zero vector looks like. 5. We have a distributive property that works with scalars multiplied by the sum of vectors. It says c times u plus v. If you missed what I just said, just keep watching. Equals cu plus cv. This is not the distributive property you're used to. This is true for all scalars, for all real numbers c. So that's about where the similarity with the distributive property from real numbers ends. And for all u and v inside the vector space, element of the vector space. Okay, let's move this along. 6. C and D are real numbers. So that addition that you're looking at, C plus D, that's regular old scalar addition of numbers. 1 plus 2 is 3. 7 plus 9 is 16, etc., etc., etc. So C plus D multiplied by a banana, v, equals the real number c times the banana plus the real number d times the banana. Okay. Now I want to make sure you're okay with this in a second, or that at least you're sort of following along. This is true. Just give me a minute. So this is for all c and d that are scalars, and for every v in the vector space. For every v in the set. I want to ask you a question. I want you to think about this. Property 6. How many operations? Let's say this again. Let me say this again. Is this addition and this addition, are they the same kind of addition? The answer is no. C and D are real numbers. So that addition on the left is addition of scalars. This is ordinary addition of scalars. This addition on this side is addition of vectors. This is vector addition. Vector addition. It's the addition that we're defining on our set. Okay, so we're using that plus sign to indicate two very different things. You have to keep track. Okay, and you'll be able to. In the context on the left, there's only one possible thing that could be. C and D are real numbers. So C plus D is regular addition. C times V is a vector. D times V is a vector. How do I know that? Because I've started out by saying we have an operation of scalar multiplication. So C times V is a scalar multiple of a vector. It's real number times a vector. And real number times a vector stays a vector. Okay. Onward. So, 2 more properties. 7. C times dV equals CD times V. For every C and D that are real, and for every vector V in the vector space V. Okay. I want to ask you a question. I want you to think about it. in this statement number 7, how many different kinds of multiplication are there? How many different kinds of multiplication are there? How many different kinds of multiplication are there? So look on the left-hand side, d times v, a scalar times a vector. So that's the new operation of scalar multiplication. There's one. Then that other c times dv, that other c on the left, that other operation of multiplication on the left. Well, if d times v is a vector, then c times it is also c times a vector. So there's only one type of multiplication on the left. How about on the right? On the right, there are two kinds of multiplication. C and D are real numbers. This is ordinary multiplication of scalars. However, that operation right there between C, D, and V, this is scalar multiplication of vectors. That's our new multiplication. Okay, so there are two operations, two different operations of multiplication here. Both are being represented by the same notation, namely no notation at all. We put the two quantities next to each other. That's called juxtaposition. Juxtaposition. That means putting two quantities next to each other and interpreting that there's an operation of multiplication that's taking place. And I want to get rid of that though, because it's not part of our definition. One more thing has to hold true. You're going to get used to these eight properties. They look familiar to you because real numbers behave like that. However, these are not real operations. Okay, these are brand new operations. 1 times v equals v for every vector in the vector space. 1 times v equals v. That times on the left is not multiplication of two real numbers, because v could be a banana or a lamp or a chair or a car or the moon, whatever your vectors are. Okay, 1 times a moon, 1 times a banana, okay, etc., etc., etc. Okay. By the way, a special note, and I hate to have to say this, but your author makes a lot of mistakes in this section. I'm going to try to warn you about the mistakes as we go through, to all the mistakes as we go through. The first mistake he does in this is he writes 1 dot v equals v. This is what your author writes. This is your author's number 8, and this is very bad. There's no definition of dot in this. This is very, very bad. This is very, very, it's not just bad, it's very, very bad. In every other part of the definition of a vector space, there's no dot. Suddenly introduces a dot. No. We have to be obsessive with the notation. So that's a mistake in our textbook. Okay. Okay. So let's take a before we dig into seeing how these vector spaces work. Let's take a look at a few notes, a few things that we're going to have standard, or things I'd like to say about vector spaces before we dig in. So, first note, the elements from our vector space V are called vectors. So the first thing I want to note is the elements of our vector space are called vectors. The scalars that we use to multiply are just regular real numbers. But the elements in our set V are called vectors. Next, very often boldface print is used to designate vectors. This is going to be familiar for physics folks or Calc 3 students or students who've had Calc 3. Boldface are used to designate boldface print is used to designate vectors, or arrows if written. And what I mean by that is if you want the vector u in a textbook, you'll see it written in boldface print. So you can see how this would be impractical for writing. So for writing, we would write u, regular u, with a little arrow over it. And in Calc 3, I insist that my students use arrows when they want to represent vectors. If they don't put a little arrow over u and they want it to be a vector, it's wrong. Okay, in this course, we lighten up a little bit. So what do I mean by we'll lighten up a bit? We will not, in our course, we will not need to use arrows. There's no need for you to write arrows over your vectors. We will not need to use arrows and boldface print. We will use the letters U, V, and W to represent vectors, and the letters A, B, small a, small b, small c, small d for real number, for real numbers or scalars. So if I write A times U, then automatically, unless it's stated differently, we automatically assume that that A is a real number or scalar. Remember, scalars and real numbers mean the same thing. And that U is a vector, just because we're reserving U, V, and W for vectors and A, B, C, and D for real numbers, okay? Okay. So what about 0 versus the 0 vector? If there's a problem deciding whether 0 is a vector or a scalar, then put an arrow over it if you want it to be the vector. Or if you see it in type, or if you're typing, type 0 as boldface, then it means vector. And this really goes for vectors in general. If you're not sure, or if you'd rather put arrows over your vectors, that's okay, but you don't have to. I'm not going to, unless I need to emphasize something. I'll put an arrow that something's a vector. I'll put an arrow over it. Okay, same with you. Okay, so if I write something like 0, 0, what are these zeros? 0 times 0. What are these zeros? They're either both real numbers, because we get to assume all the properties of real numbers exist for us, unless we're trying to prove something about those properties. But we get to assume that all the properties of real numbers, that's going to be a big deal real soon. Could it mean anything else? Yeah. We have in our definition of a vector space scalar multiplication of a vector. That means scalar real number times vector. So this is possible for the both zeros to be the real number 0, or the first 0 to be a scalar and the second one to be a vector. Okay, if there's a problem understanding if you have a problem understanding that, you can simply write, if you want the second 0 to be a vector, you write 0 times the 0 vector. What does this mean? It's meaningless. It is meaningless. This has no meaning for us. Some of you are going to study a whole other part of mathematics called tensors. Tensors and vectors are examples of these more general things called tensors. And they have their own multiplications where this kind of symbol is allowed. But for us, there's no such thing as vector, vector put next to each other. No such thing at all. No such thing. Okay? Okay. So let's take a look at our first problem with vector spaces. This first problem with vector spaces is designed to get you acquainted with how the properties of the vector space behave. Okay? So here's the example. Show that I want to show that something is a vector space. I want to show that a particular set is a vector space. I want to show that R2 is a vector space. So what is R2? You know what R2 is. It's the xy plane. But we're going to define it so it looks a little differently at first. R2 for you right now means the set of all ordered pairs, x and y. Well, we're going to change this up a little bit. R2, it's still going to be the x, you can still interpret it as the xy plane, but it is the set of all 2 by 1 matrices with real numbers, with real entries. Okay? If you forgot about that M notation, this means this is the set of all column vectors xy. That's really why we call them column vectors now. This is the reason, such that x and y are real. So our points in the xy plane are now these quantities xy. We make no distinction between the ordered pair 2, 1. We make no distinction between that and the column vector 2, 1. Okay? Okay, for our course. Okay, in other courses, you make no distinction in this course also. So in other settings, the vector from physics, let's say 2i plus j, you can interpret that as the column vector 2, 1. Okay, so this is all context driven. Okay. In any case, we're gonna assume that points in the xy plane are now column vectors. This is very common, okay? I want to show that R2 forms a vector space. Forms a vector space. What's missing? Well, R2 is definitely not an empty set, so there's a non-empty set. There has to be two operations, and if you want to show that something's a vector space, you have to state what your two operations are. So forms a vector space under what two operations? Under the usual operation of a matrix addition. Matrix addition. So under the usual operations of matrix addition and scalar multiplication. This step you cannot, or this part of the problem you cannot omit. Our operations can be very different than these. So I'm starting out with a very simple vector space. Well, I want to start by showing that this is a vector space. So the set of all points in the xy plane form a vector space. So the points in the xy plane, this is almost heresy in Calc 3 to say that a point in the xy plane is a vector and was forbidden in that. Well, no, it's not. Points in the xy plane can be considered part of the vectors in a particular vector space. Okay, so I want to show that we have a vector space. I have 8 things to show. I have 8 things to show. The first one is that, remember, the first one says that u plus v equals v plus u. Okay, so I need to show that u plus v, that's the first property. I just copied it from above and turned it red. That's the first property I have to show for every u, v, and v in the vector space. So I'm going to pick an arbitrary, 2 arbitrary elements from the vector space. So let's do this. Let's let u equal 1 vector. Let's call it x1, y1. And let's v be another one. And x2, y2. Let's let both of those things be from the vector space. And let's show that when we add them up, the order doesn't make any difference. That when you add u plus v, you get v plus u. So let's u plus v. Brute force, u plus v. That's x1, y1 plus x2, y2. What's our addition? It's ordinary vector addition. Ordinary matrix addition, x1 plus x2, y1 plus y2. You're experts at vector or matrix addition. I need to show that this equals ultimately v plus u. Now look at those entries inside this matrix. x1 plus x2, those are real numbers. y1 plus y2, those are real numbers. You get to assume all the properties of real numbers. In particular, real numbers commute by addition. Real numbers satisfy the commutative property of addition. So this is the same as the matrix whose entries are x1 plus x2 plus x1 and y2 plus y1. Why? Again, just regular real operations. Real operations. Now this matrix can be torn apart into x2, y2 plus x1, y1. Why? By the definition of matrix addition. And that result is v plus u. So u plus v equals v plus u. There are no steps missing, and there are no extra steps. Each step is absolutely important to have. Next property. Property 2. Yes, this is a very slow process. I won't be doing many of these examples, so that's the good news. The bad news is you will be on homework and stuff. So, 2. Sorry about the humor there. Let's define a third point, or a third vector. Sorry, not a third point. Third vector w equals x3, y3. I want to show that u plus and then v plus w equals u plus v, and then add w after. So I'm going to use u and v as in number 1. So u plus v plus w, extremely tedious, is u plus v plus w, parentheses are absolutely everything here. Order and parentheses are everything, just like they were on your last exam, okay, for a particular matrix property. You cannot leave out parentheses, okay, unless order is understood. Well, okay, so look in the parentheses. We have the ordinary addition. So this is x1 plus x2, y1 plus y2. So that is the result of u plus v. And then we tack on x3, y3. Now we're adding two matrices together. x1 plus x2 plus x3, y1 plus y2 plus y3. Now, I need to somehow force this to equal u plus the quantity v plus w. That means those parentheses in that matrix need to be moved around. And I can do that. I'd like you to think about why. I'm going to move the parentheses. I'd like you to think about why this is okay. Why can I move these parentheses? Why? Think about that. It's going to be important that you think about each and every one of these steps as you go through homework. So I want you to tell me, why can I do that? Well, the elements of this matrix are real numbers, and we get to assume all the properties of real numbers. That's why. Real numbers satisfy the associative property of addition. That's why we can do that. So keep going. I can tear this apart, this matrix apart by matrix addition. This is the result of adding the matrices, column vector x1, oops, oh, x1, y1, that's fine. And column vector x2 plus x3, y2 plus y3. Okay. Okay. Well, what I just realized is that I started with the wrong side. So I'm gonna, in actuality, I'm gonna take probably 5 minutes to fix this, but you're only gonna take probably 5 seconds to see the change. I started out with the right-hand side, and I need to start with the left-hand side. So there, video magic. I started with the wrong side. On the left-hand side, we start with the vector u plus v plus w in parentheses. So I put in red where the parentheses should have been in my correction here. So the first line, we replace u, v, and w by their vectors. In the red parentheses on the right, we add the vectors x2, y2, and x3, y3 column vectors. Then we perform the addition of those two remaining vectors, keeping parentheses where they should be. Then within the parentheses, within the matrix, within this matrix, we can move the parentheses from the right to the left because of properties of real numbers. All the x's and all the y's are real numbers. Then we tear apart that result into the sum of the two matrices whose column vectors whose entries are x1 plus x2 and y1 plus y2 with the other column vector x3, y3. And keep in mind, we're heading toward u plus v in parentheses plus w. U plus v in parentheses plus w. Well, that first matrix is in fact u x1, y1 plus v. And then plus that remaining straggling column vector x3, y3. And what you're looking at is in parentheses u plus v plus w. Okay, very tedious process, depending on the operation and how you define the operations of addition and scalar multiplication, and also depending on the complexity of the vector space. Well, third, I need to find a zero vector. In this case, it's not going to be too rough. Okay, so what do we do to find a zero vector? We need to find a zero vector such that v plus 0 equals v for every vector v in the vector space, small v in the vector space. So start out with a vector, small v, in the vector space. Let v equal, let's say, xy, be in the vector space. Okay, or let's be much more specific. Our vector space is R2. I have to show the existence, I have to come up with a zero vector. So the word I'm going to use is choose. I get to come up with it. Choose as the zero vector. I'm going to put an arrow there just for emphasis. Choose as the zero vector 0, the column vector 0, comma 0, or 0, 0. And show that it satisfies what it must satisfy. I need v plus the zero vector to equal v. Well, v is xy, the zero vector is 0, 0. This is regular addition of matrices. So this then is x plus the column vector x plus 0, y plus 0. In that column vector are real numbers. We get to assume them all the properties of real numbers. So x plus 0 is x, y plus 0 is y. I have shown that v plus 0 equals v. Done. I found a vector, a zero vector, and I defined it as the column matrix, column vector 0, 0, and it works. So it is a zero vector. Notice I said it is a zero vector. It is a zero vector. There's nothing in the 8 properties that say that the zero vector is unique, that there's only one zero vector. There's nothing, and that's going to be important later. There's nothing in those 8 properties that says that there's only one zero vector. There's only one zero. Okay. I'll let the cat out of the bag. There is only one zero vector. We'll have to prove it later, though. There's no statement in the first 8 properties, and the only 8 properties that says that zero vector is unique. Okay, let's move on. Property number 4. Now that I have a zero vector, I need to address the only other property that has a statement of existence of something. And there are 2 properties of vector spaces where you have to come up with stuff. You have to come up with a zero vector in number 3. In number 4, you need to come up with opposites of vectors. Okay. So for every v in the vector space, there exists an opposite. I have to find it such that v plus the opposite of v is 0. What kind of 0? This 0 means the zero vector. We don't have to write the arrow there, but we're just seeing it just for emphasis. Okay. So I'm going to start with v. Let v equal, I guess I could just say let v equal the same v in step 3. So but I'll rewrite it. Let v equal the column vector xy be an element of my vector space, thing that I'd like to be a vector space. I need to come up with an opposite. That means the word we should use, or any word similar to it, is choose or let, whatever. Let the opposite of v equal the column vector whose entries are the opposite of x, the opposite of y. Those opposites are the opposites of real numbers because our entries in our matrix are scalars. So I need v plus the opposite of v to be 0. So take v plus the opposite of v and show that it equals the zero vector. V, xy, plus the opposite of v, negative x, negative y. Those are negatives. The opposites of real numbers are called negatives. Okay. How is vector addition defined? Ordinary matrix addition. So this is x plus the opposite of x, column vector, y plus the opposite of y. Those entries are real numbers. X plus the opposite of x, that's 0. Not zero vector, just regular 0. Y plus the opposite of y is 0. I get the column vector 0, 0. That is my zero vector. Done. I've shown that every element of R2 has an opposite. That's exactly the 4th property. 5. I need a distributive property, a very specific distributive property. I need to be able to distribute scalars into the sum of vectors. Okay. I need c times the quantity u plus v equals c times u plus c times v for every real number c and for every pair of vectors u and v in the vector space. So let's do it. Let's let c be a real number and u and v as in property 1. I'm being lazy. But I want to define u and v as the column vectors like in property 1. So take the left-hand side, c times u plus v. Hopefully you're starting to see the similarity between the matrix proofs that you studied so intensely for your last exam and these proofs. And again, that's the reason why I had you do them. To get ready for these proofs. So I'm letting u and v be as in property number 1. So u was column vector whose entries were x1 and y1. V was column vector whose entries are x2 and y2. And somehow I got to get that C distributed inside. Well, in order to get that C distributed inside, I'd better add those two matrices together. Why? Why can I do this? Well, this is the definition of our addition. Ordinary matrix addition. Not only that, I have the definition of scalar multiplication as the ordinary definition of scalar multiplication of matrices. Now I'm going to get rid of a couple of parentheses here because they're not necessary. Okay. Once I add those two matrices together, there's no need for the parentheses. Okay, so this equals the column vector whose entries are C times x1 plus x2, C times y1 plus y2. Why? That's the definition of scalar multiplication in this vector space. Now I can distribute that C through both of these entries of this column vector. Why? Because both of these entries in the column vector are real numbers, and we get to assume all the properties of real numbers. I'm going to tear this apart into the sum of two column vectors. How can I do that? The definition of matrix, ordinary matrix addition. That's our vector space addition. I'm going to factor out the C's. Why? My scalar multiplication is ordinary scalar multiplication that we grew up with in chapter 1. This expression represents C times U plus C times V. So C times U plus V equals CU plus CV. Okay, sorry about that. Oops. Next, property 6. Another distributive property. Not the same one. Not the same one. This time we're adding two scalars in the parentheses and then ultimately multiplying that by a vector. Very, very different. Okay. So I want to prove that C plus D quantity times V equals CB plus DV for every real number C and D and for every vector V in R2. Well, if you're supposed to show the property for all scalars C and D, identify C and D as scalars, arbitrary scalars. So let C and D be in R, and let V equal xy. Pick something out of the vector space. Pick that out of R2. Okay, and form the left-hand side. C plus D times V. Well, I should write it all out. C plus D times V equals C plus D times the column vector xy. This is equal to the column vector whose entries are C plus dx and C plus dy. Why is that true? That's our definition of scalar multiplication in our vector space. The entries of that column vector are real numbers. We have the distributive property for real numbers, so I'm going to distribute from the right into the left x and y into C plus d. I can tear this column vector apart into the sum of two column vectors. I can factor out the C because this is the definition of scalar multiplication in our vector space. This is nothing more than CU. Oops, did I call it CV? Or CV CV plus DV. Okay, I think you're getting the idea here. This is extremely, two ideas. One, it's extremely tedious. And two, it's just a matter of brute force. Okay. Okay. Mostly the tedious thing, I think so. Okay. Anyways, an associative property, a different associative property than property number 2. This one involves scalar multiplication. So I want to show that I want to show that C times the quantity dV equals the quantity CD times V, where C and D are real and V is a vector. So start out by identifying the quantities. Let C and D be real. It's the ugliest looking R. And let V equal XY be a point in the XY plane, PR2. Okay. Start with the left-hand side. C times dV equals C times the quantity D times the column vector XY. That's V. Still within the parentheses, this is C times the column vector dx dy. That's our definition of scalar multiplication. And again, our definition of scalar multiplication, this is C times dx, C times dy. Within this column vector are real numbers. We get to assume all the properties of real numbers. In particular, we have the associative property of multiplication. Finally, if you will, factor out the CD from this column vector. Why? That's the definition of scalar multiplication in our vector space. This is nothing more than CD V. And that's exactly what we needed to prove. We needed to prove that C times the quantity dV is equal to the quantity CD times V. We did it. One more property. One more property. 1 times V equals V. This one will be pretty short. It's not necessarily short in general, but for us it's going to be short. 1 times V equals V for every vector in the vector space. So pick something out of the vector space and multiply by 1. 1 times V equals 1 times X, the column vector XY. By our definition of scalar multiplication of a matrix, this is 1x, 1y, column vector. Real numbers, 1 times a real number is the same real number, so 1 times x is x, 1 times y is y, this is v. This shows that the xy plane forms a vector space. Okay. There are some real common vector spaces, so I won't do it. I won't put you through it. But similarly, the set of all matrices, m by n matrices with real entries, is a vector space under the same operations we just used, under the ordinary operations of matrix addition and scalar multiplication. Also, f a b. Now this notation doesn't mean the function of two variables a and b. FAB is the set of all real valued functions defined on the open interval AB. This is the set of all real valued functions, like y equals x squared, y equals sine of x, y equals log of x. The set of all real valued functions whose domain, so defined on whose domain is the open interval AB. this is a vector space, is a vector space under the ordinary operations of addition and multiplication of functions. Okay. What is that set F? Well, it's a huge set. Here's the open interval AB. I'll draw a few elements or vectors from this space. Here's X, here's Y, here's 1, there's 1, it's defined on an open interval. Here's another one, I'll draw another one in red. Doesn't say anything about the functions being continuous, so let's say it has a vertical asymptote. Then it actually picks up a y value there and does that. See, the domain is from A to B, so there's another one. So it's a huge set, huge set of functions. Any function continuous or otherwise, on the interval, as long as the domain is in the open interval from A to B, that forms a vector space. Okay. Well, what does something that doesn't look like a vector space look like? So here's an example. Here's an example of a set that is not a vector space. The set is R2 again. R2, we just showed R2 was a vector space, but it was a vector space with the definition of vector addition and scalar multiplication the way I gave it. So on R2, let's say x1, y1, the column vector x1, y1 plus the column vector x2, y2. We're going to redefine addition. We can define addition any way we please. x1 plus x2, that's how we had it before, plus 1. And then this the same old y1 plus y2. This and then what about scalar multiplication and the same scalar multiplication as before? C times xy equals the column vector cx, cy. So I'm leaving the scalar multiplication the same, but I'm redefining vector addition. This set R2, the xy plane now does not form a vector space under these two operations. What has to go wrong? I want you to think about that for a minute or a second. What has to go wrong for something not to be a vector space? Well, the vector space has to satisfy all 8 properties. So if a non-empty set doesn't satisfy any one of those properties, then it's not a vector space. So at least one of the 8 properties needs to not hold for something to be a vector space. So let's figure out at least one of the properties that doesn't hold. Well, let's start from the beginning. 1, I need u plus v to equal v plus u. Let u equal column vector x1, y1, v equal column vector x2, y2. I need to determine whether u plus v equals v plus u. Well, let's figure out u plus v equals. U plus v equals x1, y1 plus x2, y2. That equals the column vector whose entries are x1 plus x2 plus 1, and then the regular old y1 plus y2. Why? Because we said so. We get to define our operations any way we please. We may not get vector spaces as a result, but we can define our operations any way we want. Okay. I'd like this to equal u plus, or v plus u. Well, the entries in this column vector are real numbers, just as they were before. Real numbers satisfy the commutative properties of addition. This is the definition of the column vector x2, y2 plus the column vector x1, y1. x1, y1, yeah. This is v plus u. Well, this is not good news for us. We're trying to show that this doesn't form a vector space. So 1 works. Well, let's dig into 2. Let's dig into 2. Let's let w equal x3, y3, and u and v as in number 1. Okay. Well, what do we need to do? We need to take a look at moving the parentheses in u plus the quantity v plus w. So let's take u plus v plus w. That is x1, y1 plus parentheses. A lot of writing. x, y, 2, 2, 3, 3. Okay, there's u plus v plus w. Keep going. This is x1, y1 plus, in parentheses, some of those two matrices are column vector whose entries are x2 plus x3 plus 1. That's how you add column vectors. Why? Because we said so. That's it. There's no other reason. Now I'm adding 2 more column vectors. How do you add column vectors together in our space? Take the first entry plus the second entry. Is that it? No. You add 1. Every time you add 2 column vectors, you add 1 in the first entries, corresponding first entries. So y1 plus y2 in the second column. In the second entries, you don't. Just normal addition. Okay, so the entries are all real numbers in this column vector. So this, we can take off parentheses. This is x1 plus x2 plus x3 plus 2. This is y1 plus y2 plus y3. Somehow I got to get that equal to u plus v first and then plus w. So I'm going to do something that's very common. I'm going to stop that side and I'm going to go to the other side. I'm going to take u plus v plus w and try to force it to equal what I have above the dotted line. Let's do it. We don't have to do this all in one string of operations. So here's, it's the longest brackets here, not necessary. Here's u plus v plus w. x, y, x, y, x, y, 1, 1, 2, 2, 3, 3. Okay. Add the 2 first in the parentheses. You get x1 plus x2 plus 1, y1 plus y2 plus column vector x3, y3. So how do we add matrices? We add the first entry plus the second entry and then add 1. And for the second entry, we have y1 plus y2 and then plus y3. Just as before, this is just a column vector with real entries. So get rid of the parentheses, x1 plus x2 plus x3 plus 2. It's looking like what we need, y1 plus y2 plus y3. They're equal. Compare. parentheses on v and w, parentheses on u and v. They are the same. Okay. So u plus v plus w equals u plus v, and then plus w. Well, that was a lot, just to show that it works. Well, we got to keep going until we find something that doesn't work. Otherwise, we have a vector space. 3 and 4, remember, these are existence properties. These are properties where we have to find something. We have to find 0 in number 3, and we have to find opposites in number 4. We have to find a 0 vector in property 3. Property 3, I need a 0 vector such that v plus 0 equals v for every v in the vector space. Okay, I don't know what that 0 vector looks like. So identify it. Let the 0 vector be, I don't know what it is. So let's say 01, 02. I don't know what the entries are. So I need this. So I'm identifying it. I need the 0 vector, so I'm identifying. So I need v plus 0 to equal v. Well, how do you add matrices together? X plus 0 sub 1 plus 1, y plus 0 sub 2. And I need that to equal xy. So what do I need to choose for the first entry in my 0 vector? So 0, O sub 1 needs to be equal to, how am I going to get the first entry, x plus 0 sub 1 plus 1 to equal x? I need to have O1 or 0 sub 1 equal negative 1. And 0 sub 2 needs to be just plain old 0. So choose as my 0 vector, this is the first really strange thing happening with vector spaces. My 0 vector is the column vector negative 1, 0. Note, the 0 vector is not equal to the 0 vector in our other space. In our previous R2, where the definitions of addition and scalar multiplication were very different. Okay, so I found, as soon as you find a 0 vector, you're done with 3. Well, now I need opposites. So 4. What do I need? I need for every v in the vector space v, for every v in the vector space, there exists an opposite of v in there, same vector space of course, such that v plus the opposite of v is the 0 vector. Okay, so let v equal xy. Pick something out of the vector space. I don't know what the opposite is. I have to find it. So let the opposite of v equal, I don't know what it should be. Let's put in some placeholders for it. Let's the opposite of v equal the column vector AB. And set up an equation that says what A and B have to satisfy. V plus the opposite of v needs to equal the 0 vector. V plus the opposite of v is xy. That's known to us. Plus the unknown opposite, AB. I'm looking for the opposite of v. I'm looking for what a and b should be as related to x and y. So this is x plus, column vector x plus a plus 1, and then y plus b. Okay, and I need this to equal the 0 vector. So let's figure out what has to happen with a and b. I need x plus a plus 1 to equal -1. How come? Well, I gotta have the corresponding first entries in this column vector to equal to each other, and the second column also has to equal. The second entries have to equal corresponding entries. So that says that a should equal, we'll subtract, look at the first equation, subtract x plus 1 from both sides. So a should equal -x minus 2, and b should equal -y. As soon as I have found those two quantities, a and b, I've found my opposites. The opposites should be the column vector whose entries are -x, take away 2, and -y. We're done with that property. So just so you can see that it works, what's v plus the opposite of v? Just you don't have to do this, but let's show that v plus the opposite of v is 0. Well, v is xy. The opposite of v is -x, take away 2, and -y as a column vector. Now add these two up. This is x plus -x minus 2 plus 1, and y plus the opposite of y. These are just real numbers. It is a column vector with real number entries. Look at when you add the first entry together. Combined like terms, you get -1, y plus the opposite of y is 0. That is the 0 vector. V plus the opposite of v is the 0 vector. It's some strange stuff for people who've never seen this before. Okay, so far this thing is looking like a vector space. My goodness. I know it's not a vector space. So at least one of these properties needs to fail. Well, we're not doing so well yet. Number 5. I need that C times U plus V equals CU plus CV for every scalar C and for every U and V in the vector space. Let's do it. Let C be a real number. And let U and V be as in number 1. X1, Y1, and X2, Y2. So let's take a look at what C times U plus V equals. It's C times U plus V. I'll put the subscripts on. 1, 1, 2, 2. C times x1 plus x2 plus 1. That's how we add two column vectors in this particular space. And then y1 plus y2. Now, scalar multiplication is the same. Why? Because that's how the problem started. That's how we defined it. So this is just C times the first entry and C times the second entry. Okay. What does that equal? It equals the column vector whose entries are Cx1 plus Cx2 plus C distributing, and Cy1 plus Cy2. So that's the left-hand side. Let's take a look at what the right-hand side has to look like. The right-hand side needs to look like Cu plus Cv. So there's this little dotted line. Let's see if we can get the right-hand side to look like that. If we can, then we're heading toward a vector space. If we can't, then it's not a vector space. So this is C times x1, y1 plus C times x2, y2. That's how we're defining u and v, remember? So this is Cx1, Cy, Cy1 plus, remember the scalar multiplication is the same as it was before. It's only vector addition that's changed. So now let's add these two vectors. This is Cx1 plus Cx2 plus how much? That's a problem. The second entry is not a problem. That's a problem. Not equal. This set, the same set as we did in the last example, it was a vector space. This set is not a vector space under these new operations. So C times u plus v is not equal to cu plus cv. So again, R2 under these two operations of addition and scalar multiplication. So R2 under these two operations of addition and scalar multiplication, R2 doesn't form a vector space. Okay, it would have been really convenient if one of the earlier properties failed, because all you need to fail for something not to be a vector space is one of the 8 properties. It could turn out that only one fails, or that 7 or all 8 fail. Okay. Let's take a look at another example. Let's take a look at another common set of objects. So let's let capital S equal the set of all n by n square matrices with real entries. So let's let S equal m n by n r. Now I want to see if this is a vector space, so I'm going to need a couple of operations. So with addition, and I'm going to define my symbol for addition as plus with a circle over it, with A plus B being defined as AB. So I'm defining addition as multiplication of matrices. And the usual scalar multiplication. So the usual constant C, scalar C times matrix A. Just multiply the corresponding entries of A by C. Okay. Does this set S form a vector space? Does it form a vector space? Well, the answer is no. Can you see quickly why the answer is no? That's a pretty good hint, actually. 1. I need u plus v equals v plus u. Well, we're not using u and v now. When you're dealing with vector spaces that have a common notation for the vectors, then you could use that notation, like instead of using U and V for vectors, you can use A and B for vectors, since the vectors are matrices or purported vectors. We don't know if this is a vector space yet. So you could, instead of write U plus V equals V plus U, is that we need A plus B to equal B plus A. And it doesn't work. A plus B is AB. Now our set is huge. The set of all n by n matrices is real entries. And matrix multiplication is not commutative. So AB is not equal to BA, and BA would have been B plus A. Done. A plus B is not equal to B plus A. So S, it looks like a 5. S does not form a vector space. Of course, under these operations, this set S, the set of all n by n matrices with real entries, does form a vector space under the ordinary operations of addition and scalar multiplication, but not under these. Not under these. So that was enough to show that this thing doesn't form a vector space. I want to ask a couple of follow-up questions. I'll do that in, let's say, a different color. Is there, I don't like that color, a zero vector? Is there a zero vector? I'm going to change colors. I don't like that color. Is there a zero vector? Well, what do we need for a zero vector? We need A plus 0 equals A. Okay. We need a zero vector such that V plus 0 equals V for every V in the vector space. Okay, let's see what this looks like with our current notation. We need a zero vector such that A plus the zero vector equals A for every A in the set of all n by n matrices with real entries. Let's dig around for that zero vector. A plus the zero vector. What does that look like? It looks like A times 0. Zero matrix. Or zero vector, whatever it's going to be. And I need this to equal A. So what am I going to have to choose for my zero vector? So the zero vector is the identity matrix. Because there's only one matrix I can multiply a square matrix by and get the matrix back. So yeah, there's a zero vector. There is a zero vector. Let me ask another follow-up question. Go back to the ugly yellow. Are there opposites? Let me restate that. Let me restate that. Let's see. Do opposites exist? I don't know. Let's see. I need that for every vector in the vector space, there exists the opposite of a vector in the vector space such that V plus the opposite of V is the zero vector. That's what we need. Okay, well, let's put this in terms of the notation we have for our particular set. I need A plus the opposite of A to equal the zero vector. That's the zero vector. Okay, so this is what we need to have happen. Well, A plus the opposite of A is A times the opposite of A. That's how we define addition, is by multiplication. And this needs to equal the zero vector, I. I'm hunting for the opposite of A. I'm still looking for the opposite of A. What does the opposite of A have to be then? A times the opposite of A has to equal I. So I need the opposite of A to be A inverse. In order for opposites to exist, the opposites will have to be the inverse. Do they exist? No, not necessarily. What is our set? The set is the set. Our set is the set of all n by n square matrices. For every n by n square matrix A, the opposite of A will have to be the inverse of A. I never said that any of those matrices were non-singular. So no, they don't necessarily exist. Okay. That discussion really didn't have to take place after the number one failed. When one property fails, then it's not a vector space. You don't have to go in order either. If you're asked to determine whether something doesn't form a vector, does or doesn't, actually, let me say it this way. If you're asked to determine whether a set forms a vector space under a couple of operations of addition and scalar multiplication, all you have to do to show that we don't have a vector space is show that any one of the 8 don't hold true. If you happen to see that number 8 doesn't hold true, then state that, and it's over. Okay. I would go in order from 1 to whenever you find something that doesn't work. Just to, since you're just learning this stuff, I would go in order, but it's not necessary. Okay. We still have about 20 minutes left to go in this video segment, so and it's going to involve a bunch of proofs. So if you're up to it, go ahead and keep watching. If not, maybe take a little break and then come back in a few minutes or whenever you can. Okay. All right. The next thing I'd like to do is look carefully at a theorem in your textbook regarding vector spaces, Theorem 2.1. I sort of alluded to part of this theorem earlier. I mentioned earlier that the zero vector, there's nothing in the first 8 properties, in the only 8 properties, there's nothing in the 8 properties of vector space that say that explicitly that the zero vector is unique, that there's only one zero vector. Why can't there be 2 or 2,000 different zero vectors in a vector space? Well, it turns out there's only one. And that requires proof. That's a conjecture. That's something that's not part of the 8 properties of a vector space. So it's something that needs to be proved. Also, what about opposites? Vector spaces have opposites. And I think that was property number 5, I think. Gosh, I don't have the half of these memorized already. No, it's property number 4. Can a vector have more than one opposite? No. Well, those are two powerful statements, that the uniqueness of zero vectors and the uniqueness of opposites. So let's state the theorem and then prove it. Okay, so suppose that capital V is a vector space. The theorem says, 1, the zero vector is unique. There's only one zero vector. And 2, the opposite of a vector is unique. Zero vector is unique and opposites are unique. Let's prove it. I don't like your author's proofs. Okay, if I were you, I would stick with my proofs. He does things that I don't think he should do, and I'll be explicit with what I'm talking about as we move along. Okay, so proof. Okay, I want to prove number one. I want to prove that the zero vector is unique. That means there's only one zero vector. So a very common way of doing that. We did this with I think we did this with inverses. I think I did a proof for about the inverse of a matrix is unique. I seem to remember I did that on video lecture. In any case, it's very similar to what I did in another video lecture. If you want to show that something's unique, assume that there are two of those objects that you want to show are unique. Assume there are two and show that they must be equal to each other. So let's let 0 sub 1 and 0 sub 2 be zero vectors. Okay, I want to show that they're equal to each other. Okay, so here's the proof. 0 sub 2 equals 0 sub 2 plus 0 sub 1. Why? Every time you write a line in a proof, you should be able to explain to yourself why something is true. Okay, it's true, and in parentheses I'll write why it's true, that v equals v plus 0 in a vector space. Okay, in other words, even better, v equals v plus 0 sub 1. In other words, it's true because 0 sub 1, I'm assuming, is a zero vector, You add it to something, you don't change the thing, even if you add it to the second zero vector. Okay. Now, this also equals 0, 1 plus 0, 2. Why? Well, u plus v equals v plus u. Now, this equals 0 sub 1. Why? Because, again, of this, in parentheses, v equals v plus 0, 2. 0, 2 is a zero vector. So anything plus 0, 2 is the original thing, including 0, 1. Okay, so this is true since 0, 2 is a zero vector. It's over. I showed that 0, 2 equals 0, 1. I assume that we had two zero vectors, and I showed that they have to be equal. Okay, so zero vectors are unique. 2. Proof of 2. I want to show that opposites are unique. So pick something out of the vector space. Let's let v be in the vector space. And let's assume we have two different opposites of v. Let's let opposite of v sub 1 and opposite of v sub 2 be opposites. Opposites of the vector v. Okay. I want to show that they're equal to each other. So let's take the opposite of v, number 2. That has to equal the opposite of v, number 2 plus 0. Why? For any vector in the vector space, v equals v plus the opposite. I'm sorry, v equals v plus the zero vector. Okay. Now, I want to show that the opposite of v2 is equal to the opposite of v sub 1. I put the subscript in the wrong place here. That means I need to introduce somehow on the right-hand side the opposite of v1. Well, I'm going to do that with the help of that zero vector. The zero vector is the same thing as v plus the opposite of v. In particular, the opposite of v1. Now I've introduced on the right-hand side the opposite of V1. Now I need to get rid of everything else. Okay, well, we have all 8 properties to use. We're in a known vector space. This is the same thing as the opposite of V number 2. Opposite of V2 plus V in parentheses plus the opposite of V1. Why? That's the second property of a vector space. I can move parentheses around in vector addition. Well, this is the same thing as V plus the opposite of V number 2 plus the opposite of V number 1. Why? Property number 1. I have the commutative property of addition. Well, what's V plus the opposite of V number 2? That's the 0 vector. Why? Because the opposite of V number 2 is an opposite. And that's how they behave. You add them to the original vector, you get 0. This is equal to the opposite of V1 plus the 0 vector. Why? Property number 1. If we have a commutative property of addition, I can add in any order I want. And this equals the opposite of V1. Oops. I keep moving my... Oops. I keep moving my parentheses in the wrong place. Why? Because V equals V plus 0. So V opposite of V1 plus 0 equals opposite V1. Done. QED. I've shown that the opposite of V number 2 equals the opposite of V number 1. That means opposites are unique. Opposites are unique. Okay. So opposites are unique, and there's only one 0 vector. The 0 vector is unique. Well, we have one more theorem to look at to finish things up. I would not rely on the author's proof at all for this theorem. It's a train wreck. I'm being very blunt here. It's really messed up. Okay, it's theorem 2.2. I would rely on my proof of this theorem. So, well, which is not my proof. I didn't come up with any of this stuff. I learned this stuff years and years ago. Okay, so let V be a vector space. Okay, first, for every vector V in the vector space, what do you suppose 0 times V is? It is the 0 vector. This is not a fact. This is a theorem. This is not one of the 8 properties. None of the 8 properties directly say this, okay? This is not one of the 8 properties. So if you think it's obvious, that's a problem with your thinking. You're using the properties of real numbers to extend to vector spaces in general. And it's very common for students to do that at first. Okay, so be very careful with this stuff. The second is, for every scalar C, what do you suppose C times the 0 vector is? Is it 0 or is it the 0 vector? Well, a scalar multiple of a vector is a vector. Okay, this is also not obvious. This is also not one of the properties, 8 properties. Finally, for every vector in the vector space, what do you suppose -1 times V is? It is the opposite of V. Again, this is not one of the 8 properties. So these are conjectures. These are things that require proof. So let's prove them. Proof. First, I want to show that 0 times any vector is the 0 vector. So let's pick something out of the vector space. Let V be in the vector space. Okay. Well, the 0 vector is V. Let's see. It's 0V plus the opposite of 0V. Why? That's the property of opposites. 0V plus the opposite of 0V is the 0 vector. Okay. Okay. I'm going to do something tricky. I'm going to turn this scalar 0. These are scalar zeros that we're looking at on the right hand side. I'm going to change that into 0 plus 0. Okay, that 0 that I made into 0 plus 0, that's just a scalar 0. A real number 0. 0 is 0 plus 0, or 0 plus 0 plus 0, or 0 plus 0 plus 0 plus 0, etc., etc. Now I'm going to rewrite this as 0V plus 0V. I'm going to distribute that V on the right. Why? Why can I do that? That happens to be property number 6. That's property 6. Allows us to distribute scalars from the right in. Okay. Now, I want to rearrange those parentheses. I'm going to do it. Why? That's property 2. I can put parentheses, wrap parentheses around any two. I can move parentheses around in addition, vector addition. Well, what is the stuff in the parentheses equal to? What's 0V plus the opposite of 0V? That is the 0 vector. That is property what? That is property 4. And what's any vector plus the 0 vector? By property 3, it's the vector. Property 3. Just to be real complete here, I'll name the property above here. This is property of real numbers. And the first property is the number plus vector plus opposite. This property 4. And it's over. Look at the beginning, look at the end. I have shown that 0 times V equals the 0 vector. Okay. 2. Prove that C, a constant times a 0 vector, is 0. Very similar. Very, very similar. Okay. Let's let C be a scalar. I want to show that C times 0 vector equals the 0 vector. So the 0 vector equals C times the 0 vector plus the opposite of C times the 0 vector. Why? That's property 4 again. Any vector plus its opposite vector is a 0 vector. Now I'm going to do a similar trick that I did in that last proof, except instead of making it the scalar 0 plus 0, I'm going to make it vector 0 plus vector 0 vector plus a 0 vector. How come? Because any vector is equal to the vector plus the 0 vector, including the 0 vector itself. Okay. V plus 0 equals V. Okay, let me get rid of that. Now, you can pretty much guess what I'm going to do. I'm going to distribute the scalar C, C times 0 plus C times 0. And that is property number 5. Plus the opposite of C times 0. Move parentheses. c times 0 plus parentheses c times 0 plus the opposite of c times 0. Property 2, c, and then finally, well, almost finally, c times 0 plus the opposite of c times 0, that's the 0 vector. Anything plus the 0 vector is that vector again. Done. I've shown that c times 0, 0 vector equals the 0 vector. Okay, so let's finish this last part of the proof and finish up the lecture in the process. C. I want to show that -1 times v is the opposite of v. Okay? I want to show that -1 times v is the opposite of v. So let's start with a vector out of the vector space. Let's let v be in the vector space. What do I need? What do I need? I need to show that -1 times v is the opposite of v. Okay? Well, let's take v and add -1v to it. Let's see what happens. I'd like to get the 0 vector out of that. I have no property of the first 8. The only 8 properties of vector space. I have no way to get from this to the 0 vector right away. However, I have property number 8 that says v equals 1v. Oops. Trying to get my eraser. I have v equals 1 times v. I can also write the right-hand side is 1 plus the opposite of 1 plus -1 actually, times v. What's that? That is property number 6. Now in those parentheses on the right, those are real numbers. 1 plus -1 is 0. And what's 0v? It is the 0 vector. Why? By part 1 of this theorem. 1 of this theorem. So I would not be able to do this without part 1 of the theorem already done. Now, I claim that we're done. I claim that we're done. Let's bring down what we started with. I showed that v plus -1v is the 0 vector. So that -1v had better be the opposite of v. Why? Because opposites are unique. I just proved it. Opposites are unique. So if I find that v plus something is the 0 vector, then that something, namely -1 times v, needs to be the only thing it can be, namely the opposite of v. QED. So this brings us to the end of a very, very long section. Please get started with homework right away. The next couple of sections are also pretty rough, and I'd like you to get enough of the homework from this section done, section 2.1, before getting started on 2.2 and 2.3. It'll really help you out. So that's as far as we're going to go, and as usual, I am looking forward to talking with you all again soon.